So I will talk about flow models in kinetic form, and the short introduction and motivation is the following. So we have been working quite a lot on compartmental models, including epidemic models during the pandemics, ribosome flows and traffic flows. And in some respect, they pointed to similar directions. We know that these models are non-negative and can be written in a kinetic form. And so our interests behind this research is to study the fundamental dynamical properties, to do some generalizations if possible, to find relationships between different application fields, maybe non-biological fields. And after all, I'm originally a control engineer, so we would like to use these models and analysis results to solve control-related tasks. But I won't speak about these. Okay, so the central object of this seminar or objects are chemical reaction networks or kinetic systems. And for a control engineer, these are very general but mathematically treatable nonlinear systems. So if we take the molecules individually, then we know that these are stochastic discrete event systems, which can be represented, for example, by Petri nets. But we will mainly work on continuous concentrations. So these will be nonlinear and non-negative dynamical systems, mainly in ordinary differential equation form, but maybe in partial differential equation form. And we also know that all kinds or many kinds of complex dynamical phenomena can be captured by kinetic models. So by CRNs or kinetic systems, I mean all dynamical models that can be formally represented as a set of transformations or chemical reactions. Okay, since this is the first lecture, let us just fix the notations. So we have M species organized into complexes, which are formally the non-negative integer linear combinations of the species. And these complexes are transformed to each other through reactions. So these arrows denote the reactions between the source and the product complexes. And from these arrows and nodes, we can build a reaction graph in a straightforward way, and we can use all the graph-related notions like strong connection or weak reversibility, which are, of course, related. So let's see the dynamical models behind kinetic systems. So this is the usual one. So the differential equations look like this. So the transformations are driven by the reaction rate, and these vectors called reaction vectors show the net production and consumption, the difference between the production and consumption of molecules. Generally, I will speak about not necessarily mass action systems. So we have quite general assumptions on the reaction rate. So this should be differentiable. should have some monotonicity properties, and of course, if a molecule does not take part in a reaction, then the reaction rate, or not in a reactant complex, then the reaction rate should not depend on its concentration. A special case is the mass action kinetics, where the reaction rates are polynomial. And this is probably the most well-known mathematically. As I said, we can say that reaction networks can be considered as quite general descriptors of nonlinear dynamics. And to illustrate this, I included this figure. So if we have a not very ugly dynamical system, then we know that this can be written into so-called quasi-polynomial form, which is almost polynomial, but the exponents are not necessarily integer. And if we introduce the monomials as new variables, then the resulting dynamical system will be a Lotka-Volterra system, which is known to be a kinetic system. And from almost any non-negative polynomial system, using a simple time rescaling, we can arrive to a kinetic system. The question is whether we can use the kinetic representation for our purposes or not. Okay, after the kinetic models, a few words about compartmental models. So these models are used to represent flow of objects, mass, molecules, vehicles, people from one compartment to the other. So we have, in this figure, we have two compartments, flows between the compartments, and also flows from and to the environment. So this will be the notation. And I will use the notations of this fundamental paper here. So we will assume that these flow functions can be written into this form. Most often we can do this, and using this will be the differential equation of a general compartmental system. So outflows, flows between the compartments, and inflows. And we know that the Jacobian of such a compartmental system is very nice. This is a Metzler matrix with non-positive column sums, so we know a lot about the Jacobian of compartmental models. Of course, they are non-negative. We know that without diffusion, chemical reactions can be written into compartmental form. And we also know that generally anything can happen dynamically in a compartmental system, which means that it can also represent a wide range of dynamics. Linear compartmental systems are very nice. We know a lot about the dependence or relationship between the compartmental graph and the eigenvalues of the system matrix. We have different Lyapunov functions, the nice diagonal stability, structural controllability, observability, identifiability. So these are very nice objects. And in many cases, the graph structure alone is quite informative, not only about linear compartmental systems, but also about nonlinear ones. Okay, just one theorem about the generality of compartmental dynamics. This is in this paper with a constructive proof. I cannot go into the details, but this theorem says that basically any bounded dynamics in R ad n can be embedded into a compartmental system having n+1 compartments. And in the linear case, it's even better because through a diagonal positive transformation, any stable non-negative dynamics can be transformed into compartmental form. So this is also a general system class. Okay, so about ribosome flows. So these models appeared in the literature about 15 years ago and model the movement and information processing of ribosomes along codons. And the first such models in ODE form came as mean field approximations of a so-called asymmetric simple exclusion process, which comes from statistical physics. And these models work like this. So the density on the ICE codon segment is determined by the inflow and the outflow, of course. So this is a balance equation. And it's important that the transition rate depends both on the availability of ribosomes in the current cell and also on the amount of free space in the next one. So we can model traffic jams using these models, and also the individual sections will be of bounded capacity. Okay, so let's have a look at the kinetic interpretation of transition between compartments. It's very easy. In fact, so this is the basic kinetic model. So we have the items, objects, vehicles, and so on denoted by N, and the amount of available space in a compartment as S. And during a transition from cell I to J or compartment I to J, one object disappears from the compartment, a new object appears in the next or neighboring compartment, and it's the opposite with the spaces. So one amount or unit of space is consumed in the next compartment, and it is freed in the ICE compartment. So this is a kinetic model and can be written in a general kinetic form, where this calligraphic K denotes the reaction or transition rate between the compartment. And you can see that this depends on the concentration or number of objects and also on the amount of free space. And of course, this is a redundant state space because this is linearly, so the equation of the space linearly depends on the equation of the objects. But it's interesting that some properties can be shown in the redundant space and other properties in the reduced state space. Okay, so this is compartmental in the sense of our notations, and the capacities will be bounded. This follows from this structure. Okay, so the sum of objects and spaces is constant in each compartment, and of course we can use this relationship and write instead of the space the capacity minus the object. So this will be so-called reduced state space model, and of course we have lots of conserved quantities like the total mass. And we can define level sets also of the dynamics. Few words about how we generalized these ribosome flow models. So in the literature, mainly tubular and circular topologies were considered, and the translation rate was mass action type, which means that it was quadratic, and we generalized such models in several aspects. So we allowed an arbitrary compartmental network structure, not only tubular or circular, and a general reaction or translation rate with quite mild assumptions, and also we allowed explicitly time-varying reaction rates. What are the main properties? Of course, the solution is non-negative. It's trivial. It can be proved that the system is contractive or non-expansive in L1 norm. And if the compartmental graph is strongly connected, then the situation is very nice. We could prove the persistence of the dynamics using Petri nets. It was quite nice how we could characterize all the siphons in the Petri net. The system is strongly monotone, and each level set contains exactly one globally asymptotically stable equilibrium. This comes from the compartmental theory in the time invariant case. Okay, so a few words about stability analysis. For this, we have an additional assumption that the reaction rates can be written in this product form. And also we collect all the rates in this gamma function. So the theta is the function of the items, the nu is the function of the free space, and we collect all those in gamma, and then we can write the differential equations in this kinetic form. From this paper, we have a general logarithmic Lyapunov function of such models. In the mass action case, we get back the well-known entropy-like Lyapunov function, but if the reaction rates are more complicated and we can integrate the terms analytically, we can have a very nice other Lyapunov functions like these, for example. So let us allow the explicit time variance of the reaction rates. Of course, we have to give some form of the rates, and we chose this quite general form. So a time varying rate coefficient times theta times nu or eta in this case, and some positive denominator. So this is the general rate function. And in this case, generally we do not have equilibria, so we have to use another notion for stability. We took it from the control literature. This input to state stability is quite popular among control engineers, and basically this means that the trajectories will be contained in a ball approaching a ball of radius phi, which is a function of the time varying reaction rates or inputs if we have control systems as t goes to infinity. And also we can use so-called ISS Lyapunov functions, which are basically the same form as here to prove input to state stability. So if we have the additional assumption that these theta functions are real analytic, and this coefficient matrix which shows the graph structure of the reaction network is irreducible, then this system will be input to state stable. So this is the result of this original paper. And we can write generalized ribosome flow models as rate-controlled chemical reaction networks. So this is the basic setup, the time-varying coefficient times the other part of the rate function. But the problem is that the reaction networks are generally not strongly connected, so we cannot directly apply these results. But if we factorize the reaction rates, which is generally non-unique, then we can basically embed the equation into another kinetic form, which will be the structure of which will be isomorph to the structure of the compartmental graph. And finally, we can prove the input to state stability of the generalized ribosome flow model. So this is one possible factorization. We pick this theta and put all the other terms into the time varying coefficient. But we can try to factor out not a function of n, but n itself. And this will give another factorization, but we can also prove the input to state stability. And this also means that we have a whole family of Lyapunov functions, different Lyapunov functions for different factorizations, but all of them are good for proving stability. Okay, some words about the application to flow models or traffic flow models. For such models, we divide the road into sections, and the molecules will be the vehicles, and also we can measure or estimate the amount of free space. So the basic flow equation for traffic and other flows is here. So this is a partial differential equation where rho will be the traffic density, this F will be the flux function, R is the inflow, and S is the outflow from the road. So this is the so-called fundamental diagram of traffic flow. This is the basic relationship is that the flux is equal to the product of density and speed. And you can see here that we have some optimal flux which maximizes the number of vehicles per unit time. And after this, we go to the total congestion, which is basically a traffic jam. This is the important diagram for us. Another one which we won't really use is the speed density diagram. Okay, so if we take a not commonly used finite volume spatial discretization of flow models in this form, then we will arrive to a semi-discretized model in ODE form, where this capital F function is the numerical flux, because this is the discretized version of the PDE, the spatial discretized version. And it is easy to see that this is a generalized ribosome flow model. And also we can take the inflow and outflow as time varying rates. So all of this can be written as a ribosome flow model. So the stability results with the logarithmic Lyapunov functions can be applied to such models. It's interesting that this discretization is almost never used by traffic engineers. Okay, I have not much time left. So the relationship between the flux function of the traffic model and the reaction rate is quite transparent. So this is the reaction rate in the ribosome flow model, and we have to just multiply it with the reciprocal of the size of the road segments, and then we get the transition rate or flux of the traffic flow models. And so we proved that many of the practically used discretization schemes, including this Godunov type, which is known to be the theoretically best discretization of flow models, can be written as a generalized ribosome flow model. We did some numerical comparison, and from this you can see that so the x-axis is the number of spatial discretization points, and this is the L1 error of the solution and the L infinity error of the solution. They are not much different, and we compare different discretization schemes. So this is the Godunov, which is known to be the best. The semi-discretization is ODE, and the full discretization is also time discretized. So this is the best. The mass action discretization is between the Godunov and the Lux-Friedrichs scheme, which is also quite frequently used. So this shows that in a numerical sense, this discretization is not the best, but our purpose was not to give the best numerical scheme, but to produce or get relationship between kinetic models and traffic models. Okay, so this is the summary. Ribosome flow models can be obtained at least from 3 sources: statistical physics, the kinetic modeling of compartmental transitions, or the finite volume spatial discretization of PDE models. And all of these point to the same direction. We generalized ribosome flow models in several respects, and possibly they lose biological meaning because of the generalization. And we also showed that traffic flow models with practically any flux density function can be written as generalized ribosome flow models. So thank you very much for your attention, and I show some related publications.